Hi, welcome to PreCalculus. I am Mr. Lumanglas, or you can call me Mr. Loom. So this is our canvas, and I told you you got a welcome letter from me, and you should always start with the modules. Start here, fall 2021. You'll see the syllabus, the welcome letter, uh, meet your professor, and everything that you need for this class, and also how to create your XYZ homework account and tutoring, especially for your math lab. And there is a meet and greet discussion that is due this week, and also some orientation quiz. So for this week, we're going to focus the first 4 sections of chapter 1. Chapter 1 is all about the functions, and you will see here all the readings and the guided lectures with the videos of each section. So when you click on this, like 1.1, functions and function notation, you will see 4 tabs. Introduction is the first one, then reading, and you will see a copy of section 1.1 from OpenStax. And this is very important, reading a math textbook. So it is different than other types of reading. A math textbook teaches you concepts and techniques rather than telling you a story. Is not always the best strategy to start from the beginning and try to read every single word. If you feel like reading your math textbook is impossible, try some of the following strategies. So number one, you should always know your goal. You can see the learning objectives that we have for this chapter and for each section. Take down notes. I expect you to take down notes in your own words, working through examples. There's so many examples provided by OpenStax. Fill in the gaps, try the problems at the end of each section, and revisit the reading. And to help you reading this textbook, you can also watch videos. There are some provided videos here. Determine if a relation is a function, vertical line test, and example to determine if a table of values represents a function. And also this recorded video will be on this tab. And on the last one, practice problems, like for this one, 1.1 section 1.1 exercises. And maybe for some section, I will provide some other types of practice problems. So that's the same thing for the next section, 1.2, which is about to mean and range. 1.3. And 1.4. So this is going to be always the format of our canvas for each section. So always expect that there will be 4 sections a week if there is no quiz or there is no test within the week. So there are going to be 4 sections. So it's like in a regular semester when we are back in the classroom, expect like 2 sections a day. And then I expect you to complete your homework assignment. This is your first homework assignment, and you're going to use the XYZ homework. You should create your account. I send that to you. And yeah, for homework, I think there are 10 problems for each section. So those are good practice, especially for your quizzes and exams. Okay, so this is what we're going to finish for the whole week, 1.1 up to 1.4. And on Sunday, your first homework is 1.1, this XYZ homework. Okay, let's start the lecture. Chapter 1 is all about functions. Section 1.1 is about the functions and function notations. So this figure here, figure 1 tracks the value of that initial investment of just under $100 over the 40 years. Based on the graph here, that's from 1970 to 2010. And with this example, it shows that there is a definite relationship between the year and the stock market average. And in this chapter, we will explore these kinds of relationships and their properties. So the first one, we learn about the function, and we know that the function is a relation in which each possible input value leads to exactly one output value. So we have 3 examples here, A, B, and C. Letter A, if you notice, we have the inputs P, Q, and R, and look at the outputs M and N. So this relationship is a function because each input is associated with a single output, from P to M, Q to N, and R to N. Letter B, look at the inputs and the outputs. This relationship is also a function. In this case, each input is associated with a single output, P to X, Q to Y, and R to Z. And letter C, this relationship is not a function because input Q is associated with 2 different outputs. So Q to Y and Q to Z. So see the difference between all these 3 examples. Let's take a look for the next example. The coffee shop menu shown in figure 2 consists of items and their prices. Letter A is a price of function of this item, and letter B is the item function of the price. Okay, let's begin with letter A. So that is by considering the input as the items on the menu, and the output values are then the prices. So each item, the donut, the plain jelly and chocolate donut, has only one price. So the price is a function of all the items. So this is a function. Then letter B, 2 items on the menu have the same price, which is the jelly donut and the chocolate donut. They're the same, $1.99. So if we consider the prices to be the input values and the items to be the output, then the same input value could have more than one output associated with it. So therefore, this is not a function of a price. Next one, understanding function notation. Here, as you can see, given 31 is equal to f of January. So the output here is 31, the rule is f, and the input is the month, January. And let's evaluate the given f of x equal to x squared plus 3x minus 4 at letter A, 2, B, A, C is equal to A plus H, and D, f of A plus H minus f of A is equal to H. So for letter A, so that is substitute the x, so that is f of 2. So 2 squared plus 3 times 2 minus 4. So this is your a. And 2 squared is 4, 3 times is 6 minus 4. 4 plus 6 minus 4 is equal to 6. So f of 2 is equal to 6. Letter B. This time we use a, so f of a is simply equal to a squared plus 3a minus 4. Then letter C, a plus h. So we want f of a plus h. We want to substitute a plus h to the x. So a plus h squared plus 3 times a plus h minus 4. So expand, then simplify. So a plus h squared is a squared plus 2ah plus h squared. Then distribute 3 plus 3a plus 3h minus 4. Then combine like terms, and we'll have a squared plus 2ah oh, this is already the answer. And the fourth one, letter D, f of a plus h minus f of a over h. I'm going to use this space here. So f of a plus h, we already have that here from letter C. So that is a squared plus 2ah plus h squared plus 3a plus 3h minus 4 minus f of a. That is letter B, which is equal to a squared plus 3a minus 4 all over h. So we simplify a squared minus a squared, 3a minus 3a, negative 4, and negative negative is positive, so that is 0. So that's why this is now simply 2ah plus h squared plus 3h over h. And we're not done yet. There is a common factor of h. We factor out h, so we have 2a plus h plus 3 over h. And we simplify. So this is equal to 2a plus h plus 3. Okay. Next one. Express the relationship 2n plus 6p equals 12 as a function p equals f of n if possible. So 2n plus 6p is equal to 12. So we need to write this relationship where P is a function of N, meaning we want to write this as P equals. So we want to isolate P. And to do that, we subtract 2n both sides. 6p is equal to 12 minus 2n. And then we divide 6 both sides. Let's try to divide 6. So p is equal to 12 divided by 6 is 2. 2 divided by 6 is 1/3 n. So therefore, p as a function of n is written as, I can write it, p equals f of n, which is equal to 2 minus 1/3 of n. Okay. Next one, how do we how do we find function values from a graph? So given a parabola here, letter A, evaluate f of 2, and then letter B, solve f of x is equal to 4. So letter A, f of 2, that is, by looking at this, the point on the graph, f of 2 is 1. So that's why we have the ordered pair here, 2 and 1. So the answer is f of 2 is equal to 1. Then letter B, solve f of x is equal to 4, meaning here your y is equal to 4. So when y is equal to 4, you can draw a horizontal line here, and the points on the graph, the x values are -1 and 3. Those are the answers. Next is the vertical line test. It can be used to determine whether a graph represents a function. So all we have to do is draw a vertical line that intersects a graph more than once. Then the graph does not define a function if it's more than once. So let's check. Look at these examples here. You can draw a vertical line anywhere. So let's say here, if I draw a vertical line, as you can see here, there is on that vertical line, there is only one point that is on the graph. Anywhere you can draw a vertical line. So let's say here, and that line, you can see that there is only one point. Same thing here, there is only one point. And the other two, the second, if you draw this vertical line here, you can see that there are 2 points that are on this graph. So again, if you can draw a line anywhere, and if you see more than one point, then it is not a function. So that's why also the last one is not a function. How about the next 3 examples? Try this. Is a function? You can draw a vertical line anywhere and look at those vertical lines, you will see that there is only one point that is on the graph. So yes, this is a function. Letter B, it's a line. Let's try the vertical line test. So again, you will see that there is only one point. So yes, this is a function. And the third one, a circle. Yes, that is correct. It's not a function. So you will see here, when you draw a vertical line, there are more than one point. So that's why this is not a function. How about this one? Figure 14, does this graph represent a function? So yes. So this is actually what you call the absolute value function. So if you draw a vertical line, there is only one point that is on that graph. Next one is the horizontal test. So once we have determined the graph defines a function, an easy way to determine if it's a one-to-one function is to use the horizontal line test. So if any horizontal line intersects the graph more than once, then the graph does not represent a one-to-one function. Just like this example here, if you draw a horizontal line and you see more than one, like this, or even this, you will see here it's even more than one. So it does not represent a one-to-one function. So that is section 1.1. So next section, 1.2, domain and range. So here, given figure 1 shows the amount in dollars each of those movies grossed when they were released, as well as the ticket sales for the horror movies. So here are the top 5 grossing horror movies for the years 2000 and 2000 up to 2013. Have you seen all these movies? I Am Legend, Hannibal, The Ring, The Grudge, The Conjuring. I think I've seen all of this. And the y-axis, that's the inflation adjusted gross in millions of dollars. And the other one, the market share of horror movies by year. So in this section, we will investigate the methods for determining the domain and range of functions, such as these two. So look at figure number 2. You have the domain A, B, and C, and think that this is a function machine, and you have the range X, Y, and Z. So we can visualize here the domain as a holding area that contains raw materials for a function machine, and the range as another holding area for the machine's products. So think that domain are all the inputs and range are all the outputs. And we have here the summary of interval notations that you're going to need for this section. So we have here the first column, the inequalities, the second column, the interval notations, and how you graph it on a number line, and then the description. So look at the symbols of inequality symbols and how you write it in interval notation. So X greater than A, meaning from A up to infinity. So look at the graph, and you have to use the open and close parentheses here, or we read this as x greater than a. Same thing here, x is less than a, so that is to the left of a, so that is to the negative infinity. Then the third one, x is greater than or equal to a, so including a to the positive infinity. And the other one, let x less than or equal to a, that is from a to the left. So that's why from negative infinity to a. The next one, x is strictly between a and b. Then the next, x is between a and b to include a. So look at the interval notations. Next one, x is between a and b to include b. And the last one, including a and b. Okay, let's try this example here. Find the domain of the function f of x plus 1, f of x is equal to x plus 1 over 2 minus x. So what do we do here? So when there is a denominator, we want to include only values of the input that do not force the denominator to be 0. So we will set the denominator equal to 0 and solve for x. So that's why this will be 2 minus x is equal to 0. And then solve for x. We subtract 2 both sides. And now x is equal to 2. So here, so we exclude 2 from the domain. So that's why x could be less than 2 or x greater than 2. And using the interval notation, that is from negative infinity to 2 and from 2 to positive infinity. All right, so one thing to check about this is if you have this function f of x equal to x plus 1 over 2 minus x, that's the reason why we got 2 here. So x cannot be equal to 2. So why? So look at this. If we try to substitute 2 to x, so if we try f of 2, 2 plus 1 over 2 minus 2, 2 plus 1 is 3, 2 minus 2 is 0, and 3 over 0 is undefined. So x cannot be equal to 2. So that's why if x cannot be equal to 2, then it should be less than 2 and greater than 2. So I want you to take a look at all these using notations to specify the domain and range from 5 to 10. So you can see the inequality notations, or even using the set builder notations. Like the first one, h such that 5, that is between 5 and 10, included 10. And the very last one, to the left and to the right, meaning all real numbers. That is from negative infinity to positive infinity. Good. Next example, let's try that. Using inequality notation, set builder notation, and interval notation. So given the number line here, so let's start with inequality notation. So we have here from 1 to 3. So included 1 and 3. So that is 1 less than or equal to x less than or equal to 3. Or we have not including 5. So meaning everything that is to the right of 5 or x greater than 5. So that is inequality notation. Next is the set builder. So x such that 1 is between x is between 1 and 3. Or x is greater than 5. Okay, and the last one, the interval notation. Including 1 and 3, so that we use 1, 3 union that is from 5 to infinity. So take note of this. If these are shaded, so meaning we have to use these symbols. If not shaded, then you have to use this. About the next example, I want you to try this. Pause this and try this on your own. Give it a figure, specify the graph set to words, set builder notation, and interval notation. And I want to work on this problem. Next one is finding the domain and range from graphs. So given graph here, domain is all the x values, the inputs. So that's why we have it here from -5 up to x value is 5. And then the range is all the y values. That is from, this is the x value from -5. Oh, you can see here, this is to positive infinity. And the y values, that is from +5 down to -infinity. So how do we write that? Domain, that is from -5 to positive infinity. And the range, let's use R. That is from -infinity doesn't look good, up to +5. So this is the domain and range from the given graph. How about this? So domain D and range R. So let's start with domain, all the X values. So based on this graph, it is from here up to here. And you have an open circle here. So not including -3. So that is open parenthesis, -3 up to this value of X, which is equal to 1. And range from here, that's the lowest value of Y, to here, that's the highest. So from -4, we have points here up to, we have a point here, 0, sorry. So that is the domain and range. So don't forget, domain all the X values, range all the outputs, meaning the Y values. How about the next one? Finding domain and range from a graph of oil production. So what do we have here? Figure 11, Alaska crude oil production from here to here, and your y-axis 1,000 barrels per day. So you could say domain here is, which is the time t. Let's say this is approximately from maybe 1973. Up to, let's say this is 2010. Range. So let's say this is the lowest. Let's say that is 180. So this is 1,000 barrels. So let's use B, and highest is, this is like, that's a little above 2,000. So let's say that is 2010. So this is your domain and range. Okay. And I want you to try on your own for the next one. World population increase. So look at the X values, which is the year, and the number of people, millions of people for the Y. That is your range. Okay. Next one, I'll show you some functions and their domain and range. The first one is a constant function. Let's say f of x equal to c. Here is a horizontal line. So the domain is from -infinity to +infinity. And the range is just that constant. So that is from c to c. Next one is this identity function. And this is easy, a domain that is from -infinity to +infinity. And same thing with the range, all real numbers. Next one, this is what you call the absolute value function. F of x equal to absolute value of x. And there's no restriction on x. However, because absolute value is defined as a distance from 0 the output can only be greater than or equal to 0. So based on the graph, everything is from 0 and above. So that's why your range is from 0 to positive infinity, and domain all real numbers. Next, a parabola, a quadratic function. This is f of x equal to x squared. And again, based on this, you can see that domain is all real numbers from negative infinity to positive infinity. And this parabola opens upward, and that is from 0 to positive infinity. So that is the range. Only non-negative real numbers. Next, a cubic function. So the domain is all real numbers because the horizontal extent of the graph is the whole number line when you extend this and this. The same applies to the vertical extent. So the domain and the range include all real numbers. Next function is a reciprocal function, 1 over x. And a reciprocal function, we cannot divide it by 0, so we exclude 0 from the domain. So therefore, we write it as from negative infinity to 0 and from 0 to infinity, because x cannot be equal to 0. And the range is the set of all numbers. But not including 0. So x cannot be equal to 0. And that is the set of all real numbers that are not 0. So look at the domain and range. Next one, reciprocal squared function. Again, we cannot divide by 0, so we exclude that. So your domain is from negative infinity to 0 and 0 to infinity. And the range is from always positive, so that is from 0 to positive infinity. Square root function. We cannot take a square root of the negative real number. So that starts at 0. So the domain is from 0 to positive infinity. Same thing with the range. Next one, this is a cube root function. And both domain and range are all real numbers. Because you can try it taking the a cube root of any number, positive or negative, or cube root of a negative number that will get you an output that is negative. Next one, domain and range of given f of x equal to 2 times square root of x plus 4. So domain, x values from negative 4. So that is negative 4 to positive infinity. And the range, it starts here, go up. So that is from 0 to positive infinity. So think that if you extend this, it will go up. So that's up to positive infinity. Same thing with the domain. The next part is the piecewise function. It is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all these smaller domains. Let's start with an example here. A museum charges $5 for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for a group of 10 or more people. Write a function relating to the number of people n to the cost c. All right, so to write, so we want c of n. So museum charges $5 for a guide tour with a group of 1 to 9 people, or a fixed of 50 fee for a group of 10 or more. So 50 if it's 10 or more. And if it's below 10, that is between from 0 to 1, 0 to 9, that is 5n. So that's why, take a look at this graph here. So it is a diagonal line from 0 to 10, and then it's a flat rate of $50 if it's more than 10. So this is the piecewise defined function of this problem. Next one, the cell phone company uses the function below to determine the cost, C in dollars, for gigabytes of data transfer. So this is the piecewise defined function. C of g is equal to 25. That is from 0 to 2. Look at this graph here. And then greater than 2 is this line here, 25 plus 10 times g minus 2. And we want to find the cost using 1.5 gig of data and the cost of using 4 gigabytes of data. So 1.5, so that is C of 1.5. That's between 0 and 2, so that is equal to 25. And using 4, so that is C of 4, and 4 is greater than 2, so we have to use this 25 plus 10 times g minus 2, 4 minus 2. So that is 10 times 4 is 40 plus 65 minus 20 is equal to $45. So these are the answers. Okay. Next one. Next one, as the problem is sketch a graph of the function f of x. We have here x squared if x is less than or equal to 1, 3 if 1 between 1 and 2, and x above 2. So let's take a look at each here. So x squared is a parabola, but it stops at 1. That's why you have it here. And then a constant function from 1 to 2, which is 3, and x starting at 2, above 2. So when we combine all three, we can have this graph. So that is the graph of the given f of x. Next one is the rate of change. This describes how an output quantity changes relative to the change in the input quantity. The units and the rate of change are output units per input units. And we can solve the average rate of change, delta y over delta x, that is equal to f of x2 minus f of x1 over x2 minus x1. So let's find the average rate of change on the interval -1 and 2. So -1. So from -1 to 2, that is, you go down -3. And from -1 to 2, you also have change in g, and the change in t is equal to 3. So when you divide that, -3 divided by 3 is equal to -1. So change in g over the change in t. Here is -3. Change of t is equal to +3. So that's why this is equal to -1. How about given a table? Next example, after picking up a friend who lives 10 miles away, Anna records his distance from home over time. The values are shown below. Find the average speed over the first 6 hours. Over the first 6 hours. So given the time t and d of t. So what we do here is we have 292. Oops, where's my marker? Minus 10 over 6 minus 0. So 292 minus 10 is 282 divided by 6, and 282 divided by 6 is equal to 47. So the average speed is 47 miles per hour. So that's the average speed over the first 6 hours. Okay. How about this? Compute the average rate of change of f of x is equal to x squared minus 1 over x on the interval 2, 4. So we want to solve f of 2 and f of 4. Let's do that. So substitute 2 to x. 2 squared minus 1/2 is 4 minus 1/2 is equal to 2 times 4 minus 1 is 7/2. The other one, f of 4, 4 squared minus 1/4, 16 minus 1/4, and 4 times 16 is 64 minus 1 is 63 over 4. And we want the average rate of change So that is equal to f of 4 minus f of 2 over 4 minus 2. So this is like your f of 4 is 63 over 4 minus f of 2, 7 halves over 4 minus 2. And when you simplify this, you will get 49 over 8. Okay. So let's take a look at this next figure. So using a graph to determine where a function is increasing, decreasing, or constant. So based on this graph, you can see here that this is increasing. Oops. And this is decreasing, and again, increasing here. Look at this. Again, this is increasing part here. This is the decreasing part, and this is increasing. And we call this the local maximum 16 that occurs when x is equal to -2. So this point, -2, 16. And the -16 here is, we call it a local minimum, and that is when x is equal to +2. So we have here a 2, -16. So here, again, another example based on this. This is your local maximum. This is the increasing part, and this is decreasing. So what is a local maximum? So that is the value of the input where a function changes from increasing to decreasing, just like this. From increasing to decreasing, it changes from increasing to decreasing. That's why you will have that point, which is the maximum, local maximum. The next one is finding increasing and decreasing intervals on a graph. Take a look at the graph. Figure number 6, identify the intervals in which the function appears to be increasing. So appears to be increasing is from here to here. Do you agree? So that is from 1 to 3 and this part. That is from 4 to positive infinity. So based on the graph, those are the intervals appears to be increasing. Next one, given the graph of function f of x is equal to 2 over x plus x over 3, then use the graph to estimate the local extrema of the function and to determine intervals in which the function is increasing. So using technology, this is the graph of f of x. And As you can see, there is a low point between 2 and 3. And that is a mirror image here, which is a high point, or we call it a local maximum here. And that is somewhere between -3 and 2, between this 2 and 3. So if you want to get to estimate the local extrema, which is this part here, I'll show you actually now. Sorry. Use decimals, and if you type the given function, f of x is equal to 2 over x plus x over 3. You'll see this is our graph. And based on this, we have a local extrema here at x 2.449. So the question is when it is increasing. Sorry. Looks like it's increasing here. So that is from -infinity to -2.449, and increasing here from 2.449 to positive infinity. So if this is your first time to see decimals, all you have to do is just type the given function and you'll see the graph. Again, these are the functions with the increasing, decreasing. So with a constant, identity function, quadratic function, I want you to take a look at those when it is increasing and decreasing. Same thing with the cubic, reciprocal, and reciprocal squared. Also cube root, square root, and the absolute value function. Next one, figure number 13. Absolute minimum is at f of 2 is equal to 2 based on this, and absolute minimum is f of 0 is equal to -2. How about this one? Find the absolute maxima and minima. How do we find all the absolute maxima and minima? Okay, observe the graph. Based on the graph, you have two absolute maximum, and that is when x is equal to -2 and x is equal to +2. And what is the y value? 16. So the absolute maximum is the y coordinate at x is equal to -2 and +2, which is 16. Same thing for minima. So we have minimum at x is equal to 3. And what is the y value of that? So that is what you call the absolute minimum, which is, what is that? -10. And the last part here is composition of functions. So when the output of one function is used as the input of another, we call the entire operation of composition of functions. So for any input of x and functions f and g, this action defines composite function. So let's start with an example here. Find and simplify the functions f g of x and f minus g of x. Given the two functions f of x and g of x, f of x is equal to x minus 1 and g of x is equal to x squared minus 1. Are they the same function? F of g of x so that is multiplying the two functions, x minus 1 times x squared minus 1. And when we multiply the two, so x minus 1 times x squared minus 1. Oops, where's my marker? This one. Then the other one, f minus g of x, that is f of x minus g of x. So f of x is x minus 1 minus x squared minus 1. So remove the parentheses, x minus 1 minus x squared negative is positive 1. So that is simply x minus x squared. Okay. Go to the next one. This time using a graph to evaluate the composite function. So given here, we're going to evaluate f of g of 1. So you have g of x here and f of x. What you do here is always start inside the parentheses. So you have g of 1. So g of 1 is equal to 3. Based on the graph here, g of 1 is equal to 3. And then use that f of 3 is equal to 6. So that's why that is the answer. So f of g of 1 is equal to 6. So again, to illustrate that, g of 1, this is 1. So that is the value, which is 3. And then at 3 here, use that here. So 3 here, 3 on the graph, that is equal to 6. So that's why the answer is equal to 6. Okay, that is actually 1.4. So please, if you have any questions, you can always send me an email. Please don't hesitate to send me an email. Also, don't forget to work on your homework assignments. There are 1.1 up to 1.4. If I were you, don't wait until the weekend to start working on your homework assignment. So if I were, let's say, start every day, work on, let's say, 1.1 on Tuesday and then 1.2 on Wednesday, and so on and so forth. So not just all day, all 4 sections. So also I mentioned that there are like 10 problems for each section. Okay, so for this week, that's your assignment together with the discussion. The first one, discussion. About meet and greet discussion, and then the homework. And then next week, I think the last 3 sections of chapter 1, and also we will start our lab assignment next week. By the way, you will see my cats. I have 2 cats. This is Sophie. Say hi. All right, so that's it for this week. Thank you.